Okay, what is the capacity if channel noise is colored? So what do you mean by colored? Basically, the noise elements are not independent with each other. That is the case. So capacity of y is equal to x plus z with a power constraint. And here we have a power constraint to be equal to sum of the power, average power is less than or equal to P. So in this case, basically it is the sum of the expectation is less than or equal to N times P. So that's a little difference. It's a notational difference. It's a small thing. N times P, you can set it equal to total capacity P. And anyway, in this note, we use this notation. So, but it doesn't change anything, right? And in this case, in terms of the covariance matrix, Kx, sum of these powers is basically sum of the diagonal element of Kx. So we can just say that it is a trace of Kx. So trace of Kx is less than or equal to the total power budget. Okay, and here the crucial difference from the independent noise case is that the noise is correlated in general. So Kz is not diagonal in general. Okay, so that's the only difference. So how do we find the capacity in this case? So mutual information between x and y, again, h of y minus h of z, and that is less than or equal to this one. And we have this expression, which is the entropy of Gaussian with the covariance matrix equals to kx plus kz, right? Kx is the covariance matrix of x, and z is the covariance matrix of z. And this is achieved when y is Gaussian, and y is Gaussian if x is Gaussian. So it is achievable, okay? So we need to find the, in this case, we need to find the maximum determinant of covariance matrix of y subject to the trace constraint on Kx, which is power constraint, okay? So that's the problem. And in order to deal with this problem, we need to, decompose the Kz into a diagonal matrix. So Kz is equal to Q lambda Qt, where Q is a unitary matrix, so that Q transpose is equal to 1, or Q transpose Q is equal to 1. And this is the n by n matrix, okay? And we consider determinant Kx plus Kz, and Kx plus this diagonalization, decomposition, using this diagonalization decomposition, we have this Q lambda Qt, and we can express Kx as this, where using the unitary matrix of Q transpose is 1, Q transpose is 1, identity matrix. So basically, Kx can be represented this way as well. And once we have that, then we have common factors from the left, which is Q, and the Qt from the right. Then we can express this, and then using the determinant identity, then basically the Q and QT in terms of determinant doesn't have an effect. Basically Q, you can call it B, the rest of them equal to C, then determinant of Q times rest of them, and then we do that with the QT as well later on, but we can get rid of Q first, and then next we call this B and C, and then we can get rid of C. And then what's left is determinant of first, the determinant of this part, the center, Q transpose KX Q plus lambda, okay? And we can call this QT KXQ as A. And from here, this diagonalization, we can obtain lambda by Q transpose KZ times Q. Okay, so here, small conclusion is the determinant of KY, which is KX plus KZ, is equal to determinant of A plus lambda. Okay, lambda is obtained from decomposing KZ. Okay, so that lambda is diagonal matrix. Okay, A here is currently could be non-diagonal. Okay, so channel with okay, I'll continue with that. So this is the result that we obtained in previous page, and we talk about now trace constraint of A. Okay, so trace of A is trace of QT, KXQ, and then using this identity now, so this can be written as trace of QQ transpose KX, and basically QQ transpose is identity matrix, so it is trace of KX. So basically we can talk about the trace constraint on KX to be less than or equal to n times p. We can say that trace of A should be less than or equal to n times p. Okay, so the constraint can be written in terms of matrix A. Now we note this small conclusion here, another small conclusion. So basically, we need to talk about determinant of A plus lambda, and since this is a determinant, this is a number, single number, so that non-negative number. So we can talk about optimizing this number, and that can be optimized, upper bounded by with equality, which is a product of the diagonal element. So this one here is non-diagonal in general, and we have an upper bound in terms of diagonal element of A plus lambda. Okay, so diagonal element of A plus lambda. All right, so that's product of these diagonal element. Okay, that is what appears in the right hand side. And when the next question is, the first is this inequality make sense? Making sense. Does this inequality make sense? So I have a little hint that says it is based on chain rule. Okay, chain rule on entropy. So what does that mean? Basically, we can talk about entropy of y1, yn, or entropy of vector y, right? That's what we are talking about. And using the chain rule of entropy, this can be written as entropy of y1, entropy of y2 given y1, plus and so on and so on, and the entropy of Yn given all the previous one, Yn minus 1, right? You remember this, and this is upper bounded by entropy of Y1 plus entropy of Y2, and so on, right? All the way up to entropy of Yn. So that's what I mean by that. And then each one of them has power, which is AI plus lambda I. Okay, so that's, that's it. And if you use Gaussian, basically, if we use Gaussian, basically, we can obtain this inequality, okay? So using the chain rule of entropies, and then applying the Gaussianness of this random variable, then we can obtain this inequality. And the equality is achieved when A plus lambda is indeed diagonal. If it is indeed diagonal, equality is achieved. Okay, so using this, now we go back to the derivation that we were doing. So we were doing right here, and we apply this result, and log of determinant is upper bounded by product. So log of product is sum of logs of individuals in individual ones. So this is obtained from here to there using this result. And we work on the covariance matrix of Kg. Kg is this, can be diagonalized because it is non-negative definite matrix. And once we have that, then that is just the, we can have no effect on the unitary matrix, on the determinant. So it is determinant of lambda. Determinant of lambda is nothing but product of lambda I running from 1 to n. So we finally have combining the two logs. Basically, it is AII plus lambda I divided by lambda I in the argument of the log. So that's what we have right here. So we have upper bound going this way. All right, and basically that's it. So once we have that, I think we have equality all the time, right? Because yeah, I think we have equality all the time from this line to that line. Yeah, I think that we have equality right there. And then we have this formula again, right? That we have seen this formula in previous derivation when noise elements are independent with each other, right? Here in the previous case with the independent noise was this formula, right? Pk over nk, right? Now lambda I takes the role of nk. Here should be k. Okay. Why, if we use I, this should be I over I. Okay. All right. So it was this. Now it is this. So it is. I mean, the pi takes the role of aii, and ni takes the role of lambda I. Okay, so once we have that, then we apply the water filling solution. Okay, and then if you find these power levels, AIIs, then you apply it to the formula, then you get this. All right, so from here, I mean, these two lines are exactly the same lines that we had in the parallel Gaussian channel case, where the channel noise is independent with each other. Okay, so that's the basically it for solution for colored Gaussian noise case. So colored Gaussian noise case, all you have to do is to find AII, which is L minus lambda I. How do you get lambda I? Basically, you need to do diagonalization of KZ, and then you obtain lambda, okay? So that's it. So here is a quick summary. So what we have so far can be summarized into this single chart. So channels with a colored Gaussian noise case, we consider the problem number one, let's say P1, and we find the capacity of P2. So these two problems are equivalent in terms of capacity. So here, y is equal to x plus z, where z is Gaussian distributed with kz. Kz can be diagonalized by q lambda qt. Okay, you can find such q for non-negative definite matrix kz, and then the problem is find kx, right, with the constraint, with the trace constraint, which is power budget constraint. Okay, so that was the problem. This problem can be written this way, right? Find the capacity of this channel now. Okay, this channel. How do you obtain this channel? Basically, you apply QT. Since KZ is given to you, you can find Q, then you can apply QT to your Y, then Y is this, then QTY is nothing but QT times X plus Z, and then you can distribute the QT, then you obtain this, then you can just give a name for QT Y as Y prime, QTX X prime, QTZ Z prime. And then this channel now has noise vector Z prime, which is Gaussian distributed with a zero mean, and its covariance matrix KZ prime. KZ prime is expected value of KZ prime, which is this, and then it can be shown that KZ prime is diagonal because we have done diagonalization. Okay, so KZ prime is now diagonalized. So this channel is parallel Gaussian channel with independent noise, right? So this is parallel Gaussian channels with independent noise. Okay, independent Gaussian noise. So that is described by this, independent Gaussian noise. We know the solution for this. So once you know the solution, you apply this solution basically based on water filling solution. You find allocation on X prime. So once you find X prime, the best allocation for X prime, then you apply, once you find the solution for X prime, then you, using this transformation, you find the solution for X. So that's what we can do, okay? So here we find the best I mean you apply the you find the best kx prime satisfying this power constraint as we have done, and kx prime was a in previous previous page. Sorry about the notation, but sometimes we need to do this to get to the conclusion quickly. Okay, and once you apply the water filling solution on kx prime, and then once kx prime is a diagonal matrix with water filling powers because it is independent noise now. Once you have that, you have found kx prime, which is optimal. And then once you find kx prime, then you obtain kx by applying this. That is the end of the story. So kx prime is diagonal, but kx is non-diagonal in general. All right. So here is the complete picture. So we have this problem. Okay. So given this channel with the additive noise whose covariance matrix is given to be Kz, and this is non-diagonal in general. This is non-diagonal in general. Kz is non-diagonal in general. Find the capacity of this channel. In order to find the capacity of this channel, basically it comes down to find the covariance matrix of X. Okay, since we know how to do the optimization, in order to do the optimization, X has to be Gaussian with the zero mean and the covariance matrix Kx. So X has to be Gaussian with the zero mean and the covariance matrix of Kx. So in order to find the solution, basically all we need to do is find the Kx. Okay. In order to find the Kx, okay. Once we find the Kx, we found the solution. Okay. So given this problem to solve, we shorthandedly write it into this. So y is equal to x plus z, where z is Gaussian distributed with the covariance matrix Kz. Kz is non-diagonal in general, but since Kz is given to you, you can find a unitary matrix Q so that Kz can be diagonalized. So Q is a diagonalization matrix of Kz. Okay, so once you find Qt, you apply Qt to y, then you transform this problem, this channel into this channel. Okay, once you obtain this channel, basically this G prime is Gaussian distribution with the zero mean and the diagonal matrix of Kz. Okay, so Kz, again, if you write one more time, is this. Okay. All right. So so that's your lambda. So once you find the Q, you find the lambda since Kz is given to you. All right, and you notice that this is a parallel Gaussian channel with the independent noise. You know how to find the solution based on water filling solution. And that says your X prime has to be Gaussian with the diagonal matrix as it's a covariance matrix. So X has to be Gaussian with the mean zero, whose covariance matrix is Kx prime. Kx prime is diagonal matrix. Okay, once you have a power location done, solution found using water filling solution, so you know the diagonal element, all the diagonal element of kx prime. So you found all the diagonal element of kx prime. So you have identified the kx prime from the water filling solution. Water filling solution will give you this, right? And since you know kx prime and you know q from the diagonalization of the noise, so you can find kx for your original problem. So that's the end of story. Okay, so I have talked about parallel Gaussian channel capacities. I've covered colored noise case and independent noise case as well, both of them. Okay, I think that's the end of this lecture note. Okay.